Good afternoon. Hello. I hope you're all doing well. It's a very hot day. Last few days have been warm, and I hear this weekend's going to be hot, and next week's going to be hot, and I just want you to stay, cool in a good setting, to keep studying. I have to encourage you to keep up because the pace of the course is not going to let up. Hopefully after the test on Saturday you can take a bit of a break. I just sent you all of the notes for, actually they're not all of the notes for Module 5. I sent you the notes that I should go through today, and then I will send you more questions that you can work on for Sunday and Monday. I extended the deadline for the assignment to Saturday night. If people were unable to maneuver, they didn't realize they had to make so many answer so many questions. So that assignment those set of assignments will be due the end of Saturday, and then I guess I have to extend the other assignment. But anyway, we'll see how that goes with your prep for the material that we're doing today. I just wanted to say a few words about the test. I'm not going to spend much time on it. Some people have asked me questions. If you've asked me questions and I haven't responded, please ask me a question again, but make it in a separate email. I'm not sure how to maneuver the email application. And once you're in a thread, I just can't search for you efficiently. I can't find emails. So if you have a question, if I haven't responded to a question, write me a separate email, no forwards or anything, and I'll get back to you. There was some difficulty with communicating with the grader. Some of the tests were not sent because they were all in a long feed, and I don't know, couldn't make out. I thought I'd sent all of them, but there were a few that didn't get sent. So I did notify those students, and she will correct them before the weekend, I understand. So for test 2 will be on the module 3 and 4 material. So that is this techniques of valuation topic, and then the case analysis, the capital budgeting. Okay. I know you spent time with the TA yesterday. Anyone who didn't finish or couldn't attend the entire tutorial, make sure you watch it online. If you have additional questions, as I said, email me and I can connect with you either by phone. Oh, somebody texted me earlier and I didn't even respond. I'm sorry about that. I just remembered. Just email me again or text me again, and I'll get to you tonight. I didn't even put the timestamps in for the last video. Sorry about that, but it looks like many people went through it just the same. But I do think the timestamps are helpful. They're helpful for me to know that I've covered certain things without going through the whole video. So this topic, I've given you a summary sheet. I've put on all the kinds of techniques that we discussed. I did a bit of a summary, and hopefully you can use that and keep that at your side with your formula sheet to solve the test that's coming. So the test will be a case, and I will compartmentalize. I'll ask you for different components one at a time, and then I'll give you also additionally, I think, 5 questions from this unit. The first test was worth 10%, and I have to confirm, what did I make this test worth? So the second test is worth, I made it 10% as well. You see how nice I am? No, it's 20%. All right, it's 20%. Okay, so it's double the value. You're going to put to use everything you learned in the first week and the stuff you learned in the second week, and they'll be combined in this test. I mean, I'm not going to ask you anything but module 3 or 4, but you do need to know those techniques to answer these questions. Okay, time value of money, for instance, you need to know that stuff, and NPV. Okay, so yes, 20% for that test. Okay, so it's creeping up. So anyway, write me an email if I didn't respond to your email, and I really apologize. I need you to separately, you need to write me a new email so I can see your email, and put a nice header on it, okay? Nice subject heading that I can maybe search for test question or assignment question, etc. All right, so what I want to do today is start Module 5 because we are behind, and that's not good. I don't know what happened here. Okay. And Module 5 begins with a statistics review. I gave you review sheets. I've just sent them again. They're the same ones I sent before. And Komal Preet is asking me, do you have to attempt all 5 questions in the case? Yes. Yes, you have to do all the 5 questions and the case. So the questions I gave you, the review problems that I gave you for techniques that will prepare you, okay? And obviously the case problems I already gave you should be helpful. And you can, it's open book, so you can use them all. But hopefully you're not just copying, and you're learning and you're retaining, because you're going to need all of this material for the final exam. All right, so I want to talk about statistics. I hope this takes no longer than an hour. This should sound familiar. If it doesn't, that's okay, but please, I hope you learn it now. Statistics. These are the basics. You know, you take a whole course or 2 courses in statistics, and I just need you to know some basics, and I need you to know them very well, all right? So what is statistics about? Okay, I'll ask you the first question. What is a statistic? What is a statistic? Yes, Keaton, this is Module 5. I sent you documents, but this is the stats review, 5.1. I feel that if I do a good review, it will save us time and your confusion. But you need to be alert for this review. I'm going to expect a lot out of you, mainly that you remember what I'm saying. Okay, so what is a statistic? What is a statistic? What is a statistic? Yes, Keaton, beginning of test 3 material. We're moving on. Like I said, if you have a question or you want to talk to me, text me or email me, and I'll arrange for it. There was someone who wrote me today and I didn't call them back, but I will deal with that later. Okay, yes, answer the question. What is a statistic? Try and tell me, what is a statistic? So somebody said, Al said probability. That's not exactly it, but what is a statistic? But thank you for responding to my question. No one? What is a statistic? Is it kind of a fact? Okay, so I'm glad I'm doing this review. Is what is statistic is kind of a fact in a sense. Okay, kind of. That's kind of a good answer. Okay. Anybody else? What is a statistic? Okay, so I'm going to leave that out there. Let's talk about statistics, and then I'll ask you again. Okay, numerical evidence. Okay, you guys are getting, yes, kind of getting better. Okay, so Okay, so why do we study statistics? Maybe you'll be better at this. So what is statistics about? And then I'll get back to what is a statistic. The goal of statistics is to gain information from data about a variable so that we can better understand what to expect. So essentially, I have to tell you what a variable is, right? Mathematical analysis. So you guys are answering around the topic. Okay, so most kind of, yeah, that's better. Uses sample to study population. Okay, good. Collection, organization, analysis. Okay, much more. Okay, so I'll get back to, I'll answer that question below in the notes. You guys are all with 5.1 in front of you. So statistics, the idea is that there's uncertainty. We don't know. We don't have a crystal ball. Most of us don't have a crystal ball to know what's coming. We basically guess, right? We guess based on what's happened in the past, what we anticipate because of information that we have, right? And if we want to know something about a particular variable, a variable is a characteristic of a person or a thing that can be expressed as a number or can be converted to a number. So a variable like, I want to know how much money my company is going to make in a week. I want to know how much of a certain product will be demanded so I can order it. I want to know what the interest rate will be so I can decide whether I borrow or change or refinance my mortgage. Okay, these are variables, and I don't know what's coming, so I can gather information about a variable, and with that information I can display the information in a distribution. What's a distribution? The distribution describes the values a variable takes and how often it takes those values. Okay, so it begins with a graph. You can make a graph of a bunch of data you've collected. Okay, and you can also summarize using numbers. Okay, so those numbers from your data, where your data is a sample, so you have a variable. Let's say you want to know about sales, or let's say I want to know about the interest rate. Okay, interest rate. That's all we seem to talk about, the interest rate. Okay, and I want to know what the interest rate is going to be. I could collect information on the interest rate over the last while. Okay, so I can collect data. So let's say this is like my interest rate, or let's do it like this. So that's the rate, and this is the period. This is my observation, for instance. And in Excel, I can write down observation 1. The interest rate was 2% for a mortgage. Okay, and then the second observation, the next day the next time period I measured it, it was 1.5%. So this is information that I gather, right? And there's a bunch of information from the past. I could go from the past, or I can use information about the future to make predictions about the future. But let's say the data was like this. And what we say is that all of the information that's relevant, like within a certain time period, I could measure the interest rate over days, I could measure it over months, I can measure it over weeks, right? All of the information available on interest rates would comprise what we call the population. The population of information. The population is all of it, okay? So all we're going to do when we collect data is we get simply a sample of data. We don't get all of it. It's intractable sometimes. It's impossible to do sometimes, okay? Sometimes it's feasible. Sometimes in the physical sciences, if you want to know something about, let's say, trees in a forest, and you want to know about how tall they get, and you close off the forest and you count all the trees and you have a complete census, the entire population of trees. That's different. You can do that sometimes. But other times, you're just taking a sample, like in interest rates. It can be by, like I said, by day, by hour, by week, by month. There are all kinds of interest. So all you can do is grab a sample from there, and in that sample, you can do things. You can compute, or you can display the distribution of that variable, showing what the values are that it takes and how often it takes those values. And you can also calculate statistics. So what is a statistic? A statistic is a number. A statistic is a number that is computed from sample data intended to estimate a parameter. Oh, I have another word here. What's a parameter? A parameter is a number computed from population data that characterizes the population. Okay, so this is our goal, the parameter. We want to be able to say something about the population. Either we want to make predictions, what to expect. Sometimes we just want to describe the past, but usually want to describe the past to say or infer something about the future. Okay, often we want to just be able to do that. Sometimes we just want to know about the past. That's true. But the intention often is to make predictions about the future. So the parameter is what our goal is. And the best that we can do, if we can't get a complete census or all the population information, the best that we can do without a population is to collect a sample. It's just a part of the whole population. And we do it in a way, usually want to do it in a way that is representative. There's no systematic bias when we pick it. Like certain numbers or certain observations don't keep coming up by accident or unintentionally. So what we do with the sample is we calculate the statistic intended to estimate the parameter. So below I have some examples. So you should have seen these symbols before. The symbol mu is used for the parameter. So these are parameters here. And you guys can read this carefully. If you haven't already, you can read it later. I'm going to be kind of not rushing, but I'm going to be prancing through these notes. I'm not going to read it literally. You guys read that on your own. So these are parameters. What's a parameter? It's a measure. It's a calculation made using the full population set of data. So an example of parameters is the average. We call it the mean. The population mean universally uses this symbol. So different countries, different statistics books all over the world use this symbol for mean, because this is a Greek letter M for mean, right? So that's mu. That's the letter mu in Greek. So we use Greek letters when we're talking about the population. And then there's another measure here, the population standard deviation. The symbol is sigma. And sigma is the symbol reserved for the standard deviation of the population. This is a lowercase s, s for standard deviation in Greek. That says sigma. Now, look at here. So the population mean is going to be hard to find in a lot of cases because we don't have all of the possible information on a variable. For instance, if I wanted to know about the opinion of everybody, that's another measure. The variable I'm interested in is I want to know the opinion of everybody about whether schools should reopen. Okay, so that's not a mean or anything, but That would be a population proportion. I'm not going to talk about that right now, but the population proportion also has a symbol, and that's like a P. But we're not going to talk about that much in this course, but I like to talk about it because it's memorable. Because often when you hear about statistics, it's opinion polls and market surveys and things like that, right? So the population parameter would be population proportion P, and it's estimated. We often use the symbol P hat for the sample. So you might have seen these symbols before. So let's say, let's stick with the mean. So let's say we wanted to know about the average income of first-year students, or average income of finance students. Let's just say that. Okay, so average income of all finance students, and I just used this class to find the income of you. Then if I just use this class, I would be calculating as a substitute, estimating the population. It's not a really good estimate, but I could do that and just ask, take an anonymous survey of your incomes and calculate the average. That symbol for the class would be X bar. You see these, we've gone away from the Greek letters back to the alphanumeric symbols. So the sample mean is meant to estimate the population mean. The sample standard deviation, similarly, if you don't know what a standard deviation is, we're going to talk about that, so don't worry. That's another parameter. The population standard deviation is a parameter, and it's estimated by the sample standard deviation. So this would be all students, and this would just be one class of students. So all I really need you to remember from this is that statistics, I'm going to make it bigger. Statistics are computed from samples. You see the two S's? But parameters are computed from populations. Now the word parameter gets used and abused, but in terms of statistics, it is our goal, right? Our goal, our wish, our dream, our wish list would be to have the parameters, but it's often not the case that we can get that. So the next best thing is to calculate a statistic from a sample, well-constructed, well-collected sample. All right, so this is the terminology we reserve for computations from a population. They're called parameters, or characteristics or measures of a population. So calculations from a population are parameters. Calculations from a sample are statistics. All right, so the question about what is a statistic, if anybody asks you, or if you want to tell somebody what a statistic is, you tell them a statistic is a number computed from a sample, from sample data. I think the "a" is not supposed to be there. From sample data, and it's intended to estimate a parameter. And they'll say, what is a parameter? And you say a parameter is a number computed from population data that characterizes the population. So average income or average hours studied in a week of students, for instance. It's hard to know all of it. Either it's expensive to ask everybody, and all the time and the staff you need to collect that information. So rather than doing that, we just use a sample and estimate statistics. The business of the statistics as a field is developing the theory to support good statistics. Like, how do we compute good statistics, good estimates, good guesses at population parameters? So let's say you have a population of interest and you've collected data, a good data set, and you then create a distribution. right? So I gave an example. Sorry, I'm going to jump over here. So here's an example. I'm jumping to the 4th page. So once you have the data, and I'm not going to ask you to do this, I'm just trying to help you remember what you've done before. You've probably done this in your stats class. You create a stem and leaf plot, right? So here are this is the stem and leaf plot for spending by customers in a grocery store. So these people have spent between $2 and $69. Remember, this is a stem and leaf, so this is the first digit, and then these are the second digits. So the numbers are like $2, and this one is 7, and the next one is 7, and the next one is 8, and the next one is 9. Okay, that's how you read that. If you don't remember, you've probably seen this before. So my point about this is, so this is a stem and leaf plot, and how did I make this? I took the data and I dropped the decimals in spending, and I just kept the whole numbers, the whole dollars spent, and put them in order, and then I grouped them so I can make a graph. So this goes from 0, 0 to 0, 4 and has 5, a length of 5. It's an interval of 5. And here is 0, 5 to 0, 9. Okay, so this is created, and I can keep going. Like, again, you don't have to do this. I'm just trying to visually stimulate your memory. So here we have a distribution. I've presented to you the values and how often they appear. This is called, these are called classes. So those are the classes. And each of them are of equal length, and I've divided them this way so that they share the first digit in each class. So these numbers in this class all share the first digit, and then this is just the second digit. Anyway, the point of this graph is to analyze it, to summarize it. So I've given it to you. How do you summarize this? What do we say about this? Well, I can turn this into a smoothed out density curve. When I do this, I'll do this again with a thicker. So I could smooth this out. It's not looking so bumpy. Let's see. I gotta go faster. Okay, so those are smoothed out. This is smoothed out. What am I doing when I smooth? When I smooth, I'm saying if I had more information, if I had all the information, the population data, I believe the pattern would remain like this. Now maybe you could argue you don't see what I see. You don't see like 3 peaks, and you don't think this is going to go so high, so you draw a different one. Let's say you personally think it should look like smooth like that. Okay, so you think that these will just fill in. These are just gaps because I didn't ask enough people. The point is that what you have here is a special kind of shape. Either way, if you have 3 peaks or just 1, this distribution is asymmetric. It's not a symmetric distribution. The shape is the first thing I look at once I've drawn the distribution, once I've put the data together. The shape is the most important thing because the shape determines which statistics should compute. Maybe it did freeze because you don't see my... Okay, I'm gonna redo this. How did I do it last time? I'll just cut this off. Thanks for letting me know. I'll break the connection and do it again. Uh-oh. I lost my Wi-Fi. I don't know why. Okay, let me try to... Okay, hold on. I'm just rebooting. It's my fault. Because I didn't do an update. It wants me to do an update. And I haven't done it because I'm scared it's going to take forever. Still booting. Okay, I think I'm back. Let's see. Let's pray. Yeah, but it's still looking funny because I've already loaded and it's not showing that. Oh no. Okay, we're back up. We're in action. Okay, well, in my haste, I lost what I wrote, but it's fine. So what I was saying was that the first thing to look for when you observe a distribution is the shape. Because the shape will determine, one minute. The shape will determine the type of statistics that you can compute. Also, the kind of variable will determine the kind of statistics you can compute. So I refer to these 5 features of the distribution as criteria, or as a systematic approach to summarizing a distribution. Okay, so you're basically summarizing information on a variable. So this would describe the variable. You would report the shape, and then depending on the shape, you compute a measure of the expected value, what to expect. And that's a measure of center. Okay, and then with the center, the expected value, usually we don't want to just talk about the value itself, the expected value. We want to talk about the behavior of the variable. Is the outcome certain? Like, so if I was expecting the next student that I asked that they study 5 hours a week, if I'm expecting that as my mean, let's say that's the average of all the students in the class, the average number of hours studied are 5 hours, but what's the range, how certain, how good is that as a guess? If there's a lot of variation around that, I wouldn't bet so much money. If I was actually a betting person, I wouldn't bet so much money that the next student I asked had been studying 5 hours a week. Did I say a week or a day? Anyway, 5 hours. So to capture that, we also compute or calculate a statistic of the spread of the distribution. Okay? And then we also mention any gaps and outliers. So those arise. That's really important because these are extreme. So what you want to be able to talk about are regularities and curiosities of your distribution. Now, I don't have to spend too much time on this because, in fact, what you're going to work with in this class are symmetric distributions, okay? Because we're in finance and we look at a broad class, a class of assets. When we look at stock, we consider them risky assets, and we consider a portfolio like a combination, or a portfolio is a combination of risky assets. Okay, so we're talking about a market portfolio. So that represents risky assets like stocks in a company. And then when we talk about this portfolio that represents all the stock, the outstanding stock and the value of that stock in the economy, that you'll see, and you'll see it in the notes. We're going to be discussing it. Hopefully we'll get to it all today. You'll see that the shape, over time, the distribution of value of the market portfolio is symmetric. Okay, so we're going to end up just talking about symmetric distributions in the class, but I just want to mention symmetric and asymmetric. So these are asymmetric distributions, and they're known as skewed. This one being right skewed because there's just a few values up here, and this one being left skewed because there's a few low values over here. Okay, so this is right skewed, there's a few high. And when do you see that? Well, a few extremely large values is common when you're talking about income. So I mentioned the income example. Okay, so they talk about the 1% or the 1% of the 1%. So there's a few multi-billionaires in North American or G8 country, and most everybody else is over here. So you see most people grouping over here. What's an example of a left skewed distribution where there's just a few low values? Oops, I lost it. Sorry about that. Sorry. I need to save this. In case I do that again, I just touched it with my wrist. Okay, so I was saying that for income, there's just a few people over here, most everybody's over here. That's just a right skewed distribution. An example where there's just a few people over here, most people over here in a distribution. An example would be school grade completed. There's very few people who haven't completed. So if you imagine along this line, I have the number of people so the school grade completed, like 0 all the way to 12 would be here. And then I include how many people in certain regions have completed that school grade. You see, most people have at least a grade 9 or 10 education, and very few have no education. So anyway, just an example of left skewed. So this is a review, and it's not necessarily finance. I'm just showing you this because really finance ends up here. We end up talking about symmetric distributions. Okay, so that's what's a symmetric distribution. Let's just talk about that for a moment, since that's where we end up. Symmetric distribution is such that there's a few, the expected value is here, and there's a few values that are higher. There's many, let's say it that way. So most of the values are within a range of the expected value. Some are higher, but equally many are lower than that expected value. Okay, so they center around and they distribute around the expected value. And then there's just a few that are much higher, but just as many that are lower. So it's very balanced. It's symmetric. It's like a mirror through the center. So height, weight measures that grade will have a symmetric distribution. So grade for standardized scores, standardized testing. So MCAT and LSAT, these standardized tests will have GMAT, will have this kind of a shape. All right, and that's what we're really going to focus on. In calculating, or when you talk about measures, so now let's talk about statistics. So we have this, what would be the statistic for the expected value? The statistics for the expected value when this distribution is symmetric would be the average. But it's also the case that the average is going to be found in this class, right? But also the other measures that we often use, the median will also be here, and the mode. So what are these three things? The mode is the most frequent class. The modal class is the one with the highest peak, and that would be right here. The median is a measure of the center of the ranked data. So if you put all the numbers in order, the one that sits in the middle of all the numbers with 50% of the observations on the left and 50% of the observations on the right. Remember, these are observations. Just think about that data we were looking at with the grocery store spending, right? Those numbers are in here. So all I've done is I've turned that shape horizontal rather than vertical. So 50% are here and here. That's the median. The mean is the average. So that's a different measure. So this is the average. And this is the 50th percentile, it's called. They're different numbers. But when the data is symmetric, they're the same. So that's the way that you can determine if a distribution is symmetric or not. You can have a computer compute these for you without a graph, and you can see if they're the same, if they're close to each other. And then you can say, well, they're close to each other and there's a lot of variation around them, so I'll say it's symmetric. However, the best way to manage data is to draw it. Okay, always try and get a depiction of your data if you can. And then look at the shape and determine what are the appropriate statistics. So the statistics that we would use for the center, the expected value, if the data are symmetric, could be any of these because they're all going to be about the same number. However, in statistics and fields of finance, we settle on the mean. It's just a convention that they talk about the mean. When data are not symmetric, when they are skewed, the mean is now different from the median, and we have to choose which one is the right measure. So let's focus on this for a moment. Now we see the modal class will be at A, so this would be the mode. And then there's two other things, right? The mean and the median. So what would C be if it was drawn like this? I didn't put any numbers here, but it will always be the case that C and B will be distinct. And one will be the median and one will be the mean. So what would C be? Does anybody know? What's C called? No one? The answer's on the page, but so C, what would C be? No one? The answer is described here. The mean is not only the average, it's a measure of expected value, but it acts like the center of gravity for the distribution. It's the balancing point of the distribution. So the mean for a distribution that is skewed will be over here. It's being placed to balance off this density, in other words, this area here with this area here. So it has to be over here. It has to be away from the mode. Oh, it can't be here, right? Oh my goodness. Do that again. It can't be here. It's going to be in a place that it balances this density here, this area, with this area, this weight. So it's going to be closer, it turns out it's going to be closer to the tail or the extreme values than the other measure that we discussed, the median. So it will always be the case that the mean will be closer to the extreme values, and the compromise between the mode and the mean will be the median. So the conclusion, the concluding statement is, if your data are skewed, you should not use the mean. The mean is pulled and it's affected because the mean is an average. The mean is the average. It's all the numbers put together to calculate it. So that means the high values will affect its calculation. The median, however, doesn't use all the values. It's all the numbers in order, and it only uses the values in the middle to calculate it. So it's not affected by extreme values. So when you hear about, that says not affected by extreme values. When you hear about income, you'll often hear about the median income, not about the mean income. Because income in a population often has a few rich people, very wealthy people, but relative to the rest. Okay, so you'll use a median because the data would be skewed. So, concluding, same thing over here. If the data is skewed this way, now A will be the mean, C will be the mode, and the compromise that we use as an expected value would be the center, B, and that's the median. Now with that says median. Okay, with that explanation then, if you're going to calculate a mean, you better be sure your data comes from a population that is symmetric, roughly symmetric. So I got cut off when I was describing here. The smoothing. Okay, I want to just say a bit about the smoothing. So when I look at a distribution and I say, okay, this is the distribution, these are all the values and how often they occur. This graph was created by putting them all in order and dividing them by class. And then I can smooth, oh my goodness, I'm going to use my finger. There. So I'm going to smooth that out either like that or like this, okay? So depending how you want to draw it, that would involve those 5 features I mentioned will determine which is the better drawing. And I'm not going to get into that right now. The point of this is, what is smoothing? What am I doing when I smooth? And this is where I got cut off, or the screen froze. When I smooth, what I'm saying is, if I had more data, and in fact, if I had the entire population set of data, I believe that the pattern would remain like this. So, in other words, all of these bumps would even out, and this would fill in here, this would fill in here, and it's just going to be one bump and then a tail and a few extreme values here, but most of them will be over here. So smoothing, whenever you see this smooth distribution, it's meant to imply that that's what we think the population looks like, given the statistics that we have, or the data, sorry, that we have. So when I do it here, that's what these curves mean, okay? So I should be calculating, if I believe that the shape is like this, symmetric, I should be calculating the mean. If I believe the shape is skewed from where the data came from, I should be calculating the median. In finance, well, at least in this course, we focus on the mean. Because we focus on the mean, we also focus as a measure of spread, we work with the standard deviation. So what's the standard deviation? Let me just say a point over here. I mentioned some other measures here in the notes of center, and we will look at this, the geometric mean. We're going to talk about this. This should look familiar to you. So this is a mean as well. But you can see when you have rates, for instance, when you have interest rates, you see these are interest rates, and the interest rate is changing. Interest rate over period 1, interest rate over period 2, all the way to interest rate over period t. And I want to know, what is the average interest rate over that period? This is how I do it. What does this remind you of? Stare at this a little bit, and what does this remind you of? Muskan asked me, when do you smooth? I'm not, you don't have to smooth. I'm just saying, when you see those smooth curves, that's what they're saying. Okay, you don't have to smooth, but whenever you see smooth distributions, you know, that's what they're implying, that you're looking at the population based on, and I'll talk about it some more, you'll understand better what I'm talking about. So my question was, what does this remind you of? Does this remind anybody of anything? What does this look like? It looks ugly, I guess, because there's this big root here, but if you look here, it looks more familiar. Alright, well, we'll talk about this later. Okay, so this is like so HPR stands for holding period rate, and we're going to talk about this later. What it is giving you it's like EPR, right? It's like exactly, interest rate conversions. This is like giving you an effective period rate over a period of time, right? I'm taking the only difference here is that rate changes. When we calculate the effective period rate, we assume the rate is the same throughout the time. That's why it looks more like this. So what we're doing is taking the holding period rate is the rate you get over a t years. So the rate changes and changes and changes. And then I want to know per year, I want to know the average. To get the average, what we're calculating is known as the geometric return, or average geometric average. Okay, so when it's with rates, you're using the factors 1 plus. Anyway, don't worry about this too much because I will talk about it again later. But I just want you to see that it's familiar to you. So just to say, I'm not going to get into all of this, but in stats, if you want to describe a distribution, you describe the 5 features. You begin with the shape. The shape determines the measure of center, and then also the spread of the distribution. You should also mention any gaps and outliers. I'm not going to describe that, I'm just mentioning it, and single and multiple peaks. And with these 5, you would make a nice report about your variable. Okay. What I want to focus on right now, though, is what is the spread? There's a variety of measures of spread. Shape will determine the appropriate measure of center and spread. I've already said if the shape is symmetric, you should use the mean. So I'm going to start, I'm going to use an example, and I'm going to teach you with this example how to use stat mode in your calculator, okay? Here's my example. Pocket money. This is pocket money spent by a student for lunch or snacks over the past week. How much money can she expect to have in her pocket in a given week? So I'm going to use the last week as a sample to represent her spending. Okay, so the pocket money that she uses up all the money. So I want to see, what can I expect, or how much can she expect to have in her pocket to spend in the future weeks. So looking at this data, now you've probably done this before, right? But I want you to stick with me. We're going to do this slowly, so maybe you'll never forget. This is the symbol for the sample mean. I'm going to give you a sample, so you're going to calculate a sample mean. The sample mean says sum, so this is also a sigma, but it's uppercase sigma, and it stands for sum. It says sum together all the observations, so x represents the variable, and I is the observation. So the values that are observed, sum them all up, and then divide by n. Whenever you see this symbol, whenever you see a summation sign with an n on the bottom, or close to n on the bottom, think of the word average. Think about the word mean or average. That'll help you a lot, because statistics is about averages and relative measures. That's what statistics is about. So you need to identify averages. And there it is. Okay, so it says sum them all together and divide by n. The symbol for standard deviation is this one. And this is what I want to spend time talking about. First, though, let's calculate the average for this data using stat mode in our calculator. So we're going to make the calculation of the mean. We're going to make the calculation of the standard deviation that depends on the mean. I'm going to explain what this is, and then we're going to use the mean and standard deviation to summarize or conclude how much this student can expect to have in her pocket for spending. All right, so here's the data. What you need to work in is a worksheet. You're going to work in the statistical data worksheet. I guess I could, should I show you my calculator? Okay, let's see. Let's try this without me showing the calculator. You're going to hit the symbol in blue, and well, mine's in blue, but it says data on your calculator. So you got to hit second data. People who have the HP calculator, this is even easier, or maybe not, I don't know. You can, if you want the notes for HP, email me. I can send you the stats information on how to use the stat mode in the HP calculator. Okay, so second data, you got it? You hit that second data, and you begin, you see the letter, or you see on your screen X01. It's asking you for the first observation. If you have the other TI, the big one, the programmable one, which I don't want you to use, but some of you are using, I suspect, you're going to use the list function. Okay, I really prefer you to work with the TI or the HP that I recommended. So you're going to say, you're going to tell the calculator, right, X01 comes up. So tell the calculator to enter, and you say down twice. Then you tell the calculator the next number, because X01 now shows up. Oh, X02, sorry, shows up. So you hit 8. Enter, down, down. Now each time you click down or you hit down, the first time you see a Y. We're going to talk about that today too, but not now. Just let it be 1. Or what is it, 0? So 8, enter, down. You're asking me if Y should be 1 or 0. Let me, hold on 1 minute. Yeah, I think Y is going to be just 1, Keaton. Does anybody want me to show the calculator? I think you can do it without me showing the calculator. So then you enter all these values. Eight, enter, down and down. 10, enter, down. 16, enter, down. And 5, enter, down. So I'm just going to clear work. I don't know, Keaton, I think it should be 0. I think it's supposed to be 0. Because if you clear work, everything is 0 in the worksheet. So second clear work, 2 enter down. It's not going to affect what we're doing here. I guess I have to show you my calculator. Okay, I'm gonna put the calculator up. It's a little bit confusing for even me to explain this. Okay, I'm going to put the calculator up. It means I have to bring this off screen. Okay, this is better. You guys see that? All right. Let's do this together. Sort of spent. Okay, so you're gonna enter 2, enter down. Okay, y is automatically 1, okay. And then just go down. Then the second one, 8, enter down, down. And then 10, enter down, down. And then, sorry Keaton, I keep changing what I'm saying because I wasn't doing it on my calculator. The fourth one, 1, 2, 16, enter down, down. So automatically once you enter X, Y goes to 1. And then 5, enter down, down. I'm done. I'm done. I leave that as 0. And then, yeah, so you just go down. It shows Y01 is 1. Yeah, just go with it. If you don't put an X, Y01 will be 0. So there's my data. I'm just going to scroll through to show you. So 1 is 2, the second is 8, the third is 10, the fourth is 16, and the fifth is 5. And then what? Everybody's got it? Now I ask for second stat, and your screen should show Lin. What does Lin mean? What do you think Lin means? Well, if you keep on scrolling, so using the arrows down, it will show you n equals 5, x bar equals 8.2, sx equals 5.3, sigma x equals 4.74, and then it starts talking about y bar. Right, so lin means linear, very good. And it tells me sy and sigma y and a and b and nothing else because I only entered x. So this is a linear what it's doing is it's computing the estimates, the statistics for a line. If you had two variables in, variable X and variable Y, it's going to compute the relationship between them. All right, and that's what we're going to talk about next. But right now we're just focused on one variable, right? So let's go through this. It shows you N is 5 observations. It tells you X bar. It also tells you SX and sigma X. What is SX and sigma X? What's the difference? So Muskan is asking me what are A and B. Those are the estimates of the y-intercept and the slope for a line relationship between X and Y, which we're going to talk about later. So don't worry about A and B right now, Muskan. Okay? So my question is, what would be, if this is the mean, 8.2, what would be the standard deviation? This one or this one? SX or sigma X? What is sigma X? What is SX? So I've shown you these symbols before. You see it's already programmed into the calculator. It's universal. These symbols are universal. Muskan, it's close, but you have half points on your response there. Okay, Leonora says SX is the sample standard deviation. Correct. So that's the sample standard deviation. And what's this? I'm going to talk about what all this means in a second. I just want to see if you guys know. So what's sigma X? It's a little bit, what's the difference? SX is bigger, sigma X is smaller. Okay, so let me backtrack a bit. Everyone's calculated it. Everyone's got these numbers. Now we just have to sort out what these numbers mean. Very good. So sigma X is population for the variable X, right? All right, so the calculator doesn't know what you want. It doesn't know what you've entered. It just took those numbers and it created statistics for you. It calculated the sample mean automatically. It calculated the standard deviation of the sample as though you've given them sample, but it's also giving you the population standard deviation in case what you really have there is representative of a census or representative of a population of information. It doesn't know. The calculator can only do so much. You have to know how to interpret the results of your calculator. The same thing with software. When you use computer software, you put numbers in and you generate statistics. You got to know which ones to pick. You could get hundreds of statistics. I mean, the computer's not going to stop you. Well, not a sophisticated one. I mean, a simple, unsophisticated computer, not a supercomputer, but just a basic SAS or SPSS output is just going to come out at you. You don't know. The computer doesn't know. You have to interpret the statistics. So that's what I'm saying here. A very simple case. So you have to choose. In our case, we know we had a sample. It was just 1 week of information. And so we use SX. But I want to talk a bit. I want to go back a little bit and ask you something. I want to ask you whether we missed a step. Did we miss a step? Should we have thought of to do something? What assumption are we making when we calculate the way we are? we missed a step. I mean, I purposely did it to make the point that I want to make now. In calculating the mean, oh, that's interesting. These won't go away. Sorry. I don't know how to get rid of those. Okay. We're stuck with them. When I calculate the sample mean, I'm making an assumption. What assumption am I making? I'm assuming what when I do this? Oh, it didn't connect, did it? It didn't connect again. We're stuck again. Dear. Okay, I'm gonna fix this. There you go. Okay, so what are we assuming when we calculate the sample mean? We've assumed that the data comes from a symmetric distribution, okay? So we've assumed that. Everybody's got that? So that's assumption that we made. No, we just want to talk about this student. We're not talking about all students. We're just talking about this student's spending. The sample is from last week, but there were many weeks before that, and that would have been the population, okay? All of the information on her pocket money. But we've just taken 1 week of information. That makes that one sample. So the question was, what are we assuming when we calculate the sample mean? We've assumed that this was symmetric. Is this symmetric? Or could you assume that the population from her spending is symmetric? Think about it. If this is Monday, Tuesday, Wednesday, Thursday, Friday, so it looks like on Monday she doesn't have that much money in her pocket. I guess she doesn't want to spend too much, or she doesn't want to, she spent money on the weekend. She doesn't want to spend too much, or she's not planning on it. This Tuesday she has $8, and then it goes up to $10. On Wednesday, Thursday, she has $16, okay? That's her peak, and then she has $5 on Friday going into the weekend. So, yeah, I mean, if you put these in order, 2, 5, 8, 10, and 16, it's not a lot of data, right? You have to just make an executive type decision and say, yeah, it makes sense that sometimes she'll have more, and then she'll sometimes have a little bit more than that. Sometimes she'll have about, $8, $9, and then there's a few times that she'll have almost nothing in her pocket. Just as many, and that's just as likely as having a lot, like double in her pocket. Okay, so that's symmetry there. If you were to, see the differences here, so just giving you an idea how to eyeball this, right? So this is like 3 between here and here, and 2. It's like you can't really make a graph with 5 I can't do this. You know, you can't really make a graph, but you can argue that that's evenly spread out. It's not a lot of data. You could say if I had more data, you'd see it, but there it is. There's 6 observations here. Sorry, this is a range of 6 for these 2 observations here, and this is a range of 8 for 2 observations over here. It's pretty balanced. Probably if I had more weeks, I would be able to see that it was symmetric, okay? So that's the assumption we made. And then we calculated the mean, and we got the mean. The mean was, from our calculator, 8.2. All we did, if we didn't use our calculator, we would have added up the values and divided by 5, because there's 5 observations. Now what we want to do is compute not just the single value, because there's quite a range here, right? She has $8, but then she can have as much as double. And then she just has $2 in her pocket. So we want to represent the range of data. And we do that because the data is assumed to be symmetric from a symmetric distribution. I can do that by calculating the standard deviation. Now, I want to take some time to look at this. This is the formula for standard deviation of the sample. And this is important because I'm going to throw a lot of formulas at you. So if you understand these 2 formulas, you're going to be doing great with the rest. So what is this? When you look at this, what do you see? What kind of things do you see here? Anything familiar? Nobody? Well, you should see that the mean is in here. So that means that the standard deviation depends on the mean. So the limitations of the mean are also the limitations of the standard deviation. So you shouldn't calculate the standard deviation unless you know that the distribution is symmetric, okay, or roughly symmetric. And here, if you just don't worry about this, don't look here, look here and here. What is this? When you see that, Andre's just, you're describing what you see, but I just want you to, like, roughly, again, we see the mean, so the mean means that it means that the S is also sensitive to extreme values, just like the mean is. So we shouldn't use standard deviation when the data are skewed, only when they're symmetric. And the second point is you see this. What's this? What did I tell you about this up here? What I told you up here was whenever you see this symbol, sigma, the sum, and you see an n or a number close to n, you should say in your mind average. So this is an average. This is the average of what? What is this? This is what we're going to talk about next, okay? So what is this? So what we want to do is compute a measure that represents how far away all the observations are from the expected value. So we want a measure of variation. We want a measure of how variable the observations are from 8.2, $8.20. Notice one of our observations is actually the mean. That's not necessarily the case all the time, right? So what we do is we say, well, why don't we just find out how many, like what is the difference between the mean and the other observations? Let's calculate this. This is the deviation from the mean. Good, Nicole. So that represents the deviation from the mean, how far away each observation is from the mean. Now, these numbers are below, this one and this one are below. Those are below, and these ones are above, and this one is just a little bit below. So let's calculate that. So again, you guys could easily fill this in, but I want to go step by step with you because I only want to do this once. 2 minus, where X bar is $8.20. Fill in this column. So this one will be negative $6.20. This one will be negative 20 cents, right, because they're below. The next one will be $1.80, then $7.80, and negative $3.20. Very good. Okay, let me know when you're done. So what we're going to do now is average these. We're going to get a measure of the average deviation from the mean. So if you were to average these, what would happen? So I'm going to, because we like the average, because we're assuming that the data comes from a symmetric population, and we're going to average them. Or the sample looks relatively symmetric. We're going to average the numbers. Just like we averaged all the numbers, we're going to average the deviations. What do you get if you average these? Now you can use your stat mode again. What do you get as an average? Junho got 0. Are you sure? Sena? Is that just a coincidence for these numbers? Or is something going on? It says the deviation from the mean would be 0. But we know it's deviating. They're not all the same number, so why are we getting 0? We know that this one is 2. That's far, and that one is they're all not the mean. So why are we getting the average deviation is 0? Why is that happening? And everyone's making the same mistake, or? So the reason why this is happening, the deviation from the mean will be 0, is because of what a mean is. Remember what a mean is. A mean is a center of gravity. The mean balances these observations, the amount of them, and their distance from the mean. So this density here, the amount of them is the height, and their distance from the mean is the length. And these one, the amount of them is the height, and the distance from the mean is the length. This area and this area are balanced around the mean. So if we're going to calculate deviations from the mean this way, what are we going to get? If we do the subtraction like we did xi minus x bar, are we going to get a positive or negative on this side? Question was, if you, for all the values over here, calculating the deviation from the mean, will it be a positive or a negative if you calculate it with this formula? Yes, positive. These will be positive because, no, sorry, negative, right? Sorry. It's going to be negative because the mean is always bigger. And the ones on the other side will always be positive. So what's going to happen is, because of the balancing point that the mean is, the values for the deviation will be negative over here and positive over here, and if you add those together you will always get 0, because they're going to be just as many total negative over here as they're going to be just as many positives over here if you were to sum them, because of the way the mean is structured. So you see, you should have known that, but many students don't, so don't feel bad if you didn't, and good for the ones who did. So this will always sum to 0. So the average will always be 0. So we cannot just take an average to understand what the deviation from the mean is, or the spread around the expected value is. We can't do it like we did just the values themselves. The problem is the negatives. So one option is we can just dump the negatives, right? We can just dump them and just care about how far away. It doesn't matter which direction, right? It just matters how far away. Like this is much more far away from $8.20, and this one's much more far away from $8.20. But this one is not. It's very close. So maybe I just care about the difference, not about the sign. So I can maybe just drop them. But statisticians didn't do that. They developed statistics that do something else to deal with the negatives. What's another way to deal with the negatives rather than just absolute values, dropping them? So rather than dropping them, statisticians square the deviations. Now, that will get rid of the negative and it will retain the magnitude of the number. So this one will still be bigger than this one. So the relative differences will be maintained. The negative will be gone. And then we can average them, right? So that's why we square them. So let's square these and put the numbers here, okay, all together. And then I'll talk about what we do next. So we square these because we have no other way to deal with the fact, that the mean will make them cancel. The fact that we're figuring out the deviation from the mean makes all the numbers sum to 0. The deviations sum to 0. And that will always happen, okay? So 0, 1, 0, 4. So here are the squared values. And now I have a question for you. So either copy those out or write them out or calculate them. Confirm my numbers. So remember, our goal is to get a measure of how spread out these numbers are around the mean. How much variation is there from the expected value? That's what question we're answering. I know it's been almost 2 hours. We're going to spend a little more time on this, and I swear we're going to save time in the long run. We're going to have to. But you can't forget anything I'm telling you right now. Okay, so you got those numbers? Now my question is, these were dollars. The deviations from the mean were dollars. Are the deviations squared from the mean in dollar units? So whatever you do to the number, you also do to the units. So my question again is, the observations were in dollars. The deviations from the mean were in dollars. What are the units for these? So the units for these are actually dollars squared. But that's really strange. Nobody knows what that is, so we don't refer to it. I don't even write it here. Notice, I don't even write down the units, because if you square the deviations, you would have to square the units. I don't write them because we don't need those. This is just a temporary fix that we adjust later by taking the square root at the end. So we need the square root to remove the squared dollars. Very good, Siam. Alright, so that's why we need this. So we're going to square it now, and then we're going to square root it later. We're going to reverse or do the inverse operation. Okay, now what do? We have the deviations from the mean in squared dollars, but I don't write that unit down. Now I'm ready to average, right? I'm going to average these. First, I'm going to sum them. Let's sum them first. You can do this whole Excel unit, you can do this whole module 5 in Excel. However, when it comes to your test, the final test, you're going to have to know how to use your calculator. So you got to practice with the calculator. The sum of these, when you add them together, turns out to be 11280 dollars squared. So what is the formula? Let's go back to the formula now. Let's see what we've done. So what we've done is we have computed the deviations from the mean, we've squared them, and we've just added them up. So I have all of this. I have all of this. Now I have to do this, the average. But notice, what you probably have, or you remember this from stats, I'm dividing by 1 less. I'm going to show you why we do that. This is the formula for the population standard deviation. Can someone tell me what number I put in here? So this is the population standard deviation. It's the square root of this thing inside. The thing inside is called the variance. Now you need to know this terminology. It's called the variance. And there's something missing here. What do I put here? So this is the population. These are the parameters. And the sample standard deviation estimates this. But because we don't have all the population data and we can't get mu, the population mean, we cannot get sigma, the population standard deviation, right? So this is estimated by that. Because, this is the formula for the population. 820 is the sample mean, but it's not the population mean, but good guess. But no, I want the mu, the population mean, which I don't have because I don't have all the data. So this is the formula if I had all of the data. Because I don't have this, and I use X bar instead, we have to pay a price. And the price is, we don't get to use n, the number of observations, in this case the number of values. So this is a capital X actually for all the values of the population. This is a small x for the sample. Alright, so for population we use capitals and we use Greek letters. For the sample we use lowercase and alphanumeric symbols. So the compensation is basically that you have to go down 1. This is degrees of freedom if you remember. We have to go down 1 from n. The effect is that when you reduce the denominator, what happens to the overall number? The overall number is a little bit bigger. So you remember on our calculators, S was bigger than sigma, right? Sigma was like 4 and S was 5 something. All right, so the calculator doesn't know which one you're doing, so it gives you both. But you want the one that's a little bit bigger. The reason is it's actually been proven empirically, like it's been studied by statisticians. By doing this and using an estimate, inside of an estimate, you lose a degree of freedom, and that's adjusted for by this. So essentially what you're doing is making the spread wider, and I'll show you what I mean when we interpret the results. So you're making the spread, it's more spread out than if you actually had all of the observations. And this is to ensure that it's a good representation of the spread or variation in the numbers. Okay, so you guys can watch that part of the video again where I explain that. But basically, what we got to do now is calculate S is equal to the square root of the sample variance up here. This was always the population variance, gives me the population standard deviation here. So the S is equal to the square root of 1 over 4, or let's say 112.8 over 4. And when you calculate that, and you take the square root, you get the result from your calculator, if you remember, or if you wrote it down, $5.31. So confirm that result, make sure you can get it, and then we're going to interpret. We're going to conclude. The conclusion is, this is how I interpret mean and standard deviation. She spends about $8.20 a day, give or take $5.31. That's how I use the mean and standard deviation. So I'm saying $8.20 plus or minus $5.31. So that makes a range of how much? What are the lower and upper limits of that? I hope you guys are following. Nobody's saying anything. So what's the lowest value? So I'm giving a range of values. That's how I use the mean and standard deviation. So the higher the standard deviation, the more spread out, the more variable the numbers are. So with the mean and standard deviation, as I calculated with the assumption that the data are symmetric, what is the range of values? Or what is the range of the values? This would be $2.89. Very good. And $13, thank you Senna and Andre, and 13.51 cents, okay? So what does this show us? In one standard deviation, and that will be the case, you'll see most of the observations in one standard deviation. How many observations fit in that range out of 5? Well, 2 does not fall in, 8 does, 10 does, 16 doesn't, and 5, so it's 3. So you see, within one standard deviation, you are seeing 60% of the observations. So it's the numbers that you use to summarize. So somebody doesn't have to look at all the data. You've given them summary statistics and said X bar and S, and they should be able to make this calculation, or you can tell them most of the observations, most of the time, she will have between $3 and $13.50 in her pocket. So this is the majority of the time, you see. Let's calculate now 2 standard deviations. Will we capture all of the data within 2 standard deviations? What would be the interval for 2 standard deviations? So to do that, you would take $8.20 and you would add and subtract 2 times $5.31. Very good. So 2 times 531 is 1062. And now you're going to add and subtract that. So this gives you minus $4.20, which doesn't make too much sense because she's never going to have negative dollars in her pocket unless she borrowed money from someone or something. And $18, right? So within 2 standard deviations, I didn't even have to make these calculations. You could basically see that you would capture in 2 standard deviations all of the observations. Right. Okay, so that's how we use the mean and standard deviation. Notice here that this distribution that we've come up with, or this distribution of these observations, the sample that we've been given, does not have that special shape that you learn about called the normal distribution, right? It doesn't seem to reflect it. I mean, maybe in approximation, but we really like the normal distribution, and we do want to talk about it a little bit just to make the point that this is not exactly normal distribution. What is a normal distribution? A normal distribution has, we'll talk about that after, okay. So if you remember the normal distribution, we'll talk about it in more detail in a bit. So this is the approach, right? If you want to say, oh, well, is my data almost normal? Well, some people would argue that this is approximately normal, but you want within 1 standard deviation 68% of the observations, within 2 standard deviations 95%, and within 3 standard deviation you want 99.7% of the observations. Our data, somebody might argue, are roughly, but the thing is, the normal distribution, the normal distribution allows for some very extreme values. You see, here we got all the data within 2 standard deviations, but the normal distribution allows some observations to be extreme. So extreme, we call those ones outside of 3 standard deviations. We say they're outliers. So you should remember some of this terminology. So it allows for those extreme values to exist, or permits them. Okay, so this is a special kind of distribution that was developed. It characterized several kinds of several variables, characteristics, phenomena, different variables. Like I mentioned before, height, weight, and standardized grades follow this kind of distribution roughly, and allows some extreme values. Okay, what you probably didn't realize was the term that I used up here when I introduced this. I refer to this as ex post or historical data. So this data was taken from the past, what happened, what already happened. So that's one way you'll see data in this course. I'll give you historical data, and you will use, assuming that you have symmetry, you'll use these formula to calculate the measure of expected value and a measure of spread. But you could also get data that looks like this. This is ex ante data. So that's how I refer to it. It stands for after, or after the fact. This data here actually, these are the same numbers I used, right? But let's say I used additional information to make predictions, and I developed over time. I got a lot of information from the past. I got some information about what to expect. I got some information on prices of goods in the cafeteria that the student could spend money on. And I come up with this. This is a distribution. This shows you, it's a discrete distribution, if you know that term. So this is actually less complicated than if I gave you a continuous distribution. This discrete distribution says that 20% of the time she'll have $2 in her pocket, 30% of the time she'll have 8, 10% of the time she'll have 10, 30% she'll have 16, and 10% she'll have 5. And these probabilities are they're probabilities. Have to sum to 1. Okay? So these are the different possible outcomes. I've limited them to 5, and I've computed their probabilities. And so what I have is a distribution already. So before I gave you a sample, but now I'm giving you what's mimics this is a distribution. And because it's a distribution, now I'm going to use the symbols for a distribution, population. This is a distribution of the population. So because of that, I'm going to use symbols that mimic a population. The mean of the population is mu, and the standard deviation of a population is sigma. So I can use these symbols, but I have to calculate things differently than before, or slightly differently. Rather than using the sample mean and sample standard deviation in the regular way, like this, I'm going to use the weighted mean and the weighted standard deviation. Weighted mean and the regular mean are related. The weighted mean is a more general case of the regular mean. Can somebody tell me what's the relationship between the regular and the weighted mean? So sometimes we can just write it like that. That's the regular mean. Trying to make a simple line. Anybody? What's the relationship between the weighted mean and the regular mean? So the more general case is the weighted mean, I said. I'll just say it's called the regular mean. No one? Let me show you wait, let's take those numbers. I'll show you here and then I'll erase it. I hope I can erase it. So let's take those numbers. 2, 8, 10, 16, and 5. I'm going to add them and divide by 5, right? That's the regular mean, correct? Okay, you guys are answering. Just a simple, I want you to answer the most simple way, the least words possible, but okay, just watch me for a second. So this is what we just did. This was $8.20, right? 8.2 was the answer. But couldn't I also write this like this? Couldn't I also write this? Oops. Why did it do that? I'm also going to write that like, I guess more complicated, but in this case it's more complicated. But couldn't I just do that? Isn't this the same as this? So, does that tell you now a better way to answer my question? So what's the relationship between the weighted and the regular mean? For the regular mean, the weights are all the same and they're all equal to 1 over n. Okay, that's the relationship between them. That's what we're doing. So it's easier here to just add them and divide by 5, because then you just do one division. But then here you would have to multiply. So these would all be 0.2. So it would be 2 times 0.2 plus 8, etc. Right? So those are the weights, 20%. And they would all be the same. So the regular mean treats every single data point as equally important. That's what's happening with the regular mean. The weighted mean gives extra significance, greater significance or greater weight to some numbers and less to others. Got it? So historically, if we have historical data, we don't have any particular reason to think one observation is more important than another. They all have the equal weight. With the ex-ante data, we've used other information, gathered together all relevant pieces of information to come up with the belief that spending on Tuesday and Thursday are more significant if these are the days of the week. Got it? If you don't get that, you're going to watch the video again. All right, so now I'm going to erase that. I need to get it out of my way. I didn't take a break today. I apologize, but I really want to get through this. I guess I have to at some point. Let's see how far I get. Oh, I erased the whole thing. That's okay. Oh no, there it is. All right, so that is the weighted mean and the relationship between the two. So I have to calculate the weighted mean first and then use it to get the deviations and then square the deviations and then sum the square deviations. You see, in this case, in this formula, just like the weighted average is just multiplying together the value by its weight and then adding them. Similarly, for the standard deviation, the average is multiplying the weight times the deviations from the mean. Remember, variance is this thing in here, just like before, and it's the average of the squared deviations from the mean. That's what it is. So this looks kind of funny to you, maybe. You haven't seen it before, or you have and you vaguely remember. But this is the formula for the weighted standard deviation. This is the weighted variance, and then this square root gives it the weighted standard deviation. So what I'm going to do is actually, I gave you the solutions for this, so you guys can do this yourself, okay? So practice, because I can't spend another half an hour. This is really important that you do it. Right now, all I need you to remember is that this is an average, okay? So it's either the x's with 1 over n is an average, or x's with the weights is also an average. And here's that weight again. So practice this and check the solution. The result is actually similar number. The interpretation is the same. So you would say this is the mean, $9.10, and the standard deviation turns out to be $5.15. You can also make an interval and interpret it. Can you do this on your calculator is the question. And if you have the HP, you can calculated weighted mean and weighted standard deviation on the calculator, but with the TI you cannot. You need to do it by hand. So practice either way, whichever calculator you have, you need to practice this, all right, on your calculators. So in a test situation, I won't give you so many values. I'll just give you a few. And you get lots of practice with this. You'll see in the handouts I sent you. Okay, so what I want to do next, so you're going to practice this on your own, all right? I just wanted to talk about the normal distribution briefly. So I said some things here. What's really neat about the normal, you guys can read through that. So essentially, this is page 7. So what we're saying is, this is a distribution, this is a histogram rather than a stem and leaf plot. This is still distribution. I could smooth this out, right, from my data, and I could say this represents the population. And what I could do is, you know, until now, well, with the other exercise, I use a stem and leaf plot, and what we did was observed like the number of observations. If you include as your height the percentage of observations, what you're getting is a relative frequency histogram. Okay, different from a regular histogram where you would have the number of observations in this bar chart. A relative frequency histogram is interesting because when I smooth it, this is my attempt at smooth. Just imagine it's smooth. So when I smooth it out, what I think about is that I believe that if I had all of the data, it would pretty much have this pattern that I've smoothed it out to be. Let me try one more time. The thicker brush. And my finger there. And what's really interesting is since the bars represent the percentage of observations under the curve, are all the bars are 100% of the observations. Okay? The normal distribution is a continuous distribution with that is symmetric. We call this the density curve. It's symmetric, it's single peaked, it only has one hump, one mound, and it's we say bell shaped. Now this is just the drawing I put here. I don't know if it's necessarily normal, but I've created a symmetric distribution with 100% of the observations under the curve. If your symmetric distribution, single peaked and bell shaped, where you find, you know, it's symmetric, so the mean, the median, and the mode are practically the same. You can calculate the mean and the standard deviation, and you can check, just like we did with the pocket money example. I checked to see if within one standard deviation 68% of the observations were found. Within 2 standard deviations, 95% of the observations were found. And if in 3 standard deviations, 99% of the observations. So it turns out that stock returns as a whole on the stock market have a normal distribution. Okay, so if you look at a broad index like the S&P 500, the TSX, the American indices, you'll find that over time they will exhibit that normal distribution. We can, I'm just going to draw that and then we're going to move on, because I'm going to have you draw it later as well. So I'm drawing a curve. Essentially, the way the curve goes is the mean is in the middle, and then within 1 standard deviation, so 1 standard deviation on each side, the curve has an inflection point and curls up like that. Okay, so just to give you an idea, if you want to draw this properly, these are equal. No. My attempt at equal width, and then like that, right? And then it has to do the same thing the other side. So, watch me struggle on this thing. So essentially, it should curve and do the same sort of thing. The inflection point should be within 1 standard deviation. Anyway, so within 1, you have 68%. You remember this? So 68% of the observations in this continuous distribution are found within 1 standard deviation, and then within 2, and like I said, I'll mention this again with stock returns. So I expect you to know how to do this with numbers. Okay? And then with 3 standard deviations, I can make 3. There should be some observations. This is really hard to draw. There should be some observations over here. That's the point. Those outliers that I talked about, extreme values. And on the other side as well. Apologize for the drawings not being so neat. Really not much I can do. Okay, so on both sides you have the outliers, and the outliers, 0.3% are extreme values or outliers. And that's the important thing about normal distribution. Okay, so they're very rare. It's with a 0.3% chance. So some questions. Kyla asked, did you say this course will only be dealing with symmetric distributions? Yeah, I'm going to focus on symmetric distributions, so don't worry about the skewed ones, median and all that stuff. Okay, so somebody wants a break. They texted me. Okay, let's take 5 minutes. We'll see you at 8:30, okay? If you have questions, you can ask me. It's okay. Okay, I'm back. I'm back, and I just want to repeat. I was chatting with Kyla. What was I saying about normal distributions? I just wanted to remind you that if a variable is believed to be normally distributed, then the chance of seeing an observation within one standard deviation of the mean, like I put no numbers here, I didn't give you example with numbers, but I will soon, okay? But essentially, this is for a continuous distribution, so there's all these different numbers are possible along this number line, okay? And there's a 68% chance, or in other words, 68% of the observations are within one standard deviation. 95% are within two. And then within three, you have almost all of the observations are within 3 standard deviations. But normal distributions allow for what are called outliers. When data is symmetric, we call observations that are outside of 3 standard deviations, we call them outliers. This is a minus here. Let me do that again. So outside of 3 standard deviation, these observations here and here are outliers. And remember, the spending data didn't have anything outside of 3, right? Within 2, we had all of the data. But here, this distribution that's normal has 0.3% outlier. So if there's 100 observations or 100 values, no, that won't make sense. It has to be 1,000. So 1,000 values, then how many outliers will there be if it's normally distributed or approximately normally distributed? There will be 3 outliers. Okay? A few here and 1 here. This is an example. How did I get 3? That was 0.003 times 1,000. Just giving you an idea of what we're saying, what I'm trying to say. Okay, so now what I want to do is look at the formula. I gave you a ton of formula sheets. Let's look at the formula sheets, and then I'll talk about the correlation. So here are your formula sheets. And I've integrated everything onto one page for you. You have lots of practice for the weekend after the test, okay? Here you have, and now I'm turning to finance. Here's some financial data. Right now I'm going to give you the data, and then in the notes for Module 5, the risk and return notes, I'm going to show you where these numbers come from. But these are returns. So this is Bell Canada Enterprise stock. These are the returns to Bell Canada Enterprise, and these are the returns to the S&P. So this is a market index. It's made up of, if you talk about the S&P 500, there's 500 companies. The top valued stock, those companies' stock is their value, and the amount of them, the amount of shares outstanding, are combined, and we refer to that as market cap, the market capitalization. So we put that together for the market cap of each of the stocks in an index. The S&P 500, there's the Dow, there's the TSX, there's a TSX S&P, there's different ones in different on different stock markets. And I've put those in different periods. I haven't mentioned what just period 1, 2, and 3. It could be by minute, it could be by day, it could be by month, it could be by year. Anyway, at this point it's just period 1, 2, 3, 4, and 5. And what I'm showing you is in period 1, when the S&P is has 15% return. So for a person who invested at the beginning of period 1, by the end of period 1, they made 15%. So for every dollar invested, they made 15 cents, right? For every $1,000 invested or $100 invested, they made $15. If they invested in the index, you can actually invest in the index. Or if you have a portfolio that mimics the index, a portfolio of several stock, that's your return over that period. At the same time, people who hold Bell Canada Enterprise stock or the company itself saw 30% returns. So investors in Bell Canada Enterprise stock, for every dollar they invested, they got 30 cents. Or every $100 they got $30. Or every $100 million they got $30 million. Okay? So that's what that means. So these are now, so until now with the statistics review, I just focused on one variable. Now I'm going to take what we did with one variable and I'm going to talk about two variables. All right. And in finance, we always put the market as the X, or the horizontal variable. So if I was going to make a scatter plot, and I gave you another handout about scatter plots. I don't know if you saw it, but we're going to talk about that. So let's make a scatter plot. I'm going to ask you, make a scatter plot where you plot X, or the market here, the market returns, and you plot Y, the Bell Canada Enterprise returns on this axis. So you always put the stock here in the Y, or the company, I'll say company, or asset. And then you always put the market index here on the x-axis. Okay, make a scatter plot. Or, yeah, make a scatter plot. What do you see? Do you know how to make a scatter plot? So you're going to put 15 here. So you're going to, mark it up. Oops. you know, make a grid. I'm doing it in the corner. Hopefully you have more space to make a grid. Does anybody, without doing that, does anybody see a pattern? Is there a relationship between these two? What is the relationship between market returns and Bell Canada Enterprise stock? Does anybody see a pattern? Okay, so either you say that BCE is 2 times or double, or S&P is half, right? There's a relationship, a direct relationship, and it's always the case. It's not approximate, it's exact. 15 times 2 is 30. 9 times 2 is 18. Very good. So, what would the scatter plot look like? The scatter plot will look like, it's just going to go up like that. Very good. So what does it mean? So I have 2 questions now. What is 1? What is the slope? And second, what is the correlation? So what is the slope and what is the correlation? That's a question mark. I get it. What is the slope and what is the correlation? And I guess the third question is, how are they related? Oh, I guess I can just talk about that. Anybody? What's the slope? What's the correlation? Well, I see a line. This makes a perfect line. So there's a slope, right? Now, it doesn't have to be perfect. This is not going to be perfect. I'm just trying to make a point. Okay. So the slope, is the relationship between these two, right? It's the doubling effect. To go from one to the other, I multiply by 2. That's the slope. So slope is 2. So what's the correlation? For slope, we use the symbol B, right? B is 2. Okay, you're telling me correlation, so the symbol for correlation is R, and you're telling me it's positive. What value is it? Anybody? What's R? So R is the correlation. What is R in general? We'll talk about that in a second. What is the measure of R? What would R be? Nobody knows? R is positive 1. Okay? R is positive 1. What is R and what is slope? So slope reflects the linear slope. How I get, if I detract, if I move off of the line, how do I get back on the line? So for every unit, let me do it over here. So what's the slope? B is a slope. B is equal to change in y over change in x, right? It means for every unit I move off of along the x-axis, to get back on the y, I have to increase 2. That's how I get from one value to the other. So if I move off 1 to get back, I have to go up 2. Rise over run. R is a measure of the direction and strength of a linear relationship between two quantitative variables. That's what R is. I've written it on the handout for scatter plots. It's possibly -1 to +1. It's an index. Perfect positive correlation is a positive line, like an upward trending line, exactly on the line. All the points have to fit. For an R that's -1, it goes in the opposite direction, down, all straight on a line. So correlation tells you how good your estimate is. If you're going to use B as an estimate of the relationship between X and Y, right? Because this is just some data. It's not everything. I just got some data here, a sample. And B is telling me how to get from one to the other, how to predict one from the other, or how one responds to the other. R is saying it happens perfectly. That's what R is. Okay, so B is the relationship. It tells you about the direction but R tells you about the direction and the strength of the relationship, and it reduces the number that's reduced to an index. So from any set of data, you always interpret it the same. The relationship here is positive and perfect. That says direction. And strength. Okay? So the strength, it tells you the same. So the B and the R will always have the same direction, positive in this case. But R also tells you the strength. The closer it is to 1 or -1, the stronger the relationship, and the more valuable, or the better the predictor that B is of that relationship. Okay, so now here are all the formula below for this case. This is the historical data case. This is past data over 5 periods, you have the x and the y, and here are the formula that you would use for both x and y. I'm going to go through them, and then we're going to do this on your calculator. So x bar, you already saw that. Same for y bar, same formula. S, you already saw this, so this could be sx, and then you could do this for sy. I can use the notation square root of the variance, and you should be fine with that. So variance is just the, before you take the square root, we call this the variance underneath. And we don't use it too much because it's in the wrong units. But it gets us the standard deviation, so that's why we give it a name. And now there's this formula that I haven't discussed yet, but you guys will tell me all about it. What is that? What is that? Very good. So, covariance. Let's take a moment to look at covariance. I want to show you. I'm going to go back a bit. Okay, what is variance? Variance if we were looking at the variance would be like this. Sometimes I just don't put the indices, okay? So don't let that bother you too much. So that's the variance. The variance, remember, is the deviation squared. I could also write it like this. You see, this is the deviation squared with no square root. That's the variance. Just the average, the somewhat like an average, but I had to do one less because of that, using a estimator in my estimator. So for historical data, these are estimates, these are statistics, right? And the deviation from the mean is squared, and then I average it. So all that the covariance is doing is looking at taking the deviation of x alongside deviation with y, the deviation from the mean of y. What it's doing is capturing whether x behaves like y or opposite from y. So let me show you. I just wanted to show you this, and now I want to go to the scatter plots, okay? And then we'll come back here. First, let's just do this in our calculators. Let's do this in our calculator first, and then I'll go deeper into this so you'll feel accomplished. So to put this in our calculators, and then we'll go back to this discussion about covariance and slopes, correlation. In your calculator, go back to data, second data, and then enter x and y side by side, and confirm that you can get these values here that we got without making any calculations, just staring at the numbers. We figured that out. So confirm you got it and let me know you got it. And then we'll go to the scatter plots. Hey, good, Senna. Anybody else? So your A should be 0. It'll show you there's no y-intercept. So for your calculator, it's telling you y equals A plus B x. A is the y-intercept and B is the slope. And R is 1. Did it tell you A, Andre? Did your calculator tell you A? So A should probably come out as 0. Just goes right through the origin. I'm trying to make that. Okay, very good. Okay, so let's go to the scatter plots and we'll come back here. Other people just keep punching it in. Okay. So 5.3, I believe, is scatter plots. So I'll wait a few minutes. Oh, I pulled up the wrong one. Oh no, because you guys don't have the... Yeah, the edits don't turn up on my file. That's what's happening. So this is a summary of correlation. When you have two variables, when you're doing two variable calculus, and the reason why I wanted you to buy at least the TI 30XA is so that you have the two variable feature, okay? So I say two variable calculus, two variable statistics. You want to have the two variable feature on your calculator, and that calculator permits it, and it's also the official calculator for exams, for the licensing exams. So you draw your scatter plot like we did, where we talked about the scatter plot, and you look at the scatter plot with X and Y, and you look for regularities and curiosities, anything special about what you're looking at. Is there a pattern? And in particular, you want to see if there's a linear pattern, because with linear patterns we can make predictions. If we can identify any pattern, we can make predictions, but we focus on teaching you linear patterns in these courses, in the lower level courses, or the initial courses, introductory courses. So you want to describe your pattern, right? Whether it's linear or nonlinear. So nonlinear means a pattern, but it's not a line. Like a pattern like that's a pattern, but it's a curved pattern. All right, and this is a pattern too. But the better pattern, so it's a very scattered thing. You prefer that the pattern be, rather than trying to estimate a line going this way, we see better clusters where there's lines going like this through the data. Okay, so this one I call curved pattern, and this one I call clustered pattern. And I just make a point when clustered might exist. You see, because the idea is that the points, the dots, the observations fit better, closer to these lines going this way than they do if I try and fit a line this way. They're very scattered around a positive sloping line. And I use the example that I gave you in the notes this was soap operas on this axis, and this is sense of well-being on this axis. And this is saying that there's two groups of people. There's people who watch a lot of soap operas, and there's people who watch less soap operas hours. Okay, so this is more soap opera hours, this is less soap opera hours. And whatever the case, if they're in the group that watches less or more they watch, the less happy they are. Okay, so this is like happiness, and happiness is going down. And this is hours of soap operas. And so how can this be if you look here in this range, they look like they're equally content. But the more soap operas they watch, the less happy they are. So I just suggest these are clusters, and you could do another variable would be introduced into this analysis, and you would say, this is possibly women watch more soap operas. Maybe it's divided by gender. Maybe it's divided by age. So you'd have to look closer to see what's going on. So the point of that is there's a line, but you only see a line going this way. And the only way you could see that is if you actually graph the data. So I encourage you to always graph. That's not finance, but that's just that's of economic interest, health interest, but that's how you would look at scatter plots. Okay, so that's curves and clustered, but there's lines in the clusters. Correlation should be calculated. Remember, you only use the average as a measure of center in specific situation when the data is assumed to be symmetric, right? Or coming from a symmetric population. In this case, correlation should only be computed if you believe you have a linear relationship. And correlation measures the direction and strength of that linear relationship. The linear relationship that you see should be between two quantitative variables. So they should be two variables that so you wouldn't calculate correlation, for instance, if you were using a categorical variable like gender. Gender wouldn't be, you wouldn't calculate correlation with income and gender, at least not the correlation we're talking about in this class. So I just gave some examples here, and I want to use this example to explain the formula for correlation, because I'm going to show you it in a second. So here is the first one. I put X on this axis and Y on this axis, and my dots go perfectly up just like we saw. So this is going to have a correlation of +1. The formula for correlation captures what I'm going to show you right now, okay? What we're going to do is we're going to think about the data into 4 quadrants. So I'm going to divide the data into 4 quadrants. Do that again. Sorry. I need to learn how to use lines more efficiently in here. There. So I'm going to divide it into 4 quadrants. Let's see if I can. Oh. Okay, we'll have to put up with that line. So there's 4 quadrants. What I've done is I've divided it into that way and into this way. So what I've done is split the data into above the mean for X and below the mean for X, and above the mean for Y and below the mean for Y. When X trends above its mean, where is Y? So your answer should be above or below the mean. So when X is above its mean, where is Y? So when X is high, in other words, Y is high. When X is low, when X is high, Y is always up here, right? Y is high. And when X is low, Y is low. It's always down here. When this pattern is perfect, when X is very high above its mean and Y is very high above its mean in the same magnitude, and X is just a little higher than its mean, and then Y is also just a little higher than its mean. When that happens in equal magnitude above and below the means, that gives you that perfect positive correlation. Okay, so the formula for R reflects what I'm talking about right now. Okay, let me write it down. I'm going to put it here. Okay, that's the best I can do. So this is the formula for R. Okay, I'll just show you. In the list of formula on 5 5.4. Let me see. Let's save this. So this is the formula for R. There's many versions, but this is one here that I was writing. So this is from the sheet that we were just looking at, 5.4, document 5.4. What is this? What this does, what the formula does, is standardizes. This is like x minus mu over sigma, isn't it? And the same for y. Y minus mu over sigma. But wait, I won't write that because that's confusing. But it's standardizing, okay? It's taking the mean from the value and dividing by standard deviation. So it's standardizing the x and it's standardizing the y. If x is above its mean and y is above its mean, you're going to get a positive and a positive. And this is going to add together a bunch of positives. When x is below its mean, you'll get a negative. And if y also trends below its mean at the same time, you get a negative. That will also give you a positive because you're multiplying a negative and a negative to get a positive. So this formula, when one is above its mean and the other one is below, when they're acting or behaving differently, they'll be opposite signs, and that's what will create negatives. Okay, the more that they happen in tandem or together, so when y is far above its mean and x is far below its mean at the same time, that will make a large negative number. So it's this pattern that it reflects what I've been talking about. Okay. This formula will pick up that pattern. So I've drawn a lot of correlations that you can let's just do one more so you can see what I'm talking about, so I can move on and finish this. Oh, no, not that. So I'm going to erase that, actually, because that looks bad. And let's draw this one. So you can just do this yourself. I'm not going to do all of them, but you can just see yourself. You see when data is scattered like this, what will the R be? I'm going to cut this in its middle, so looking this way on the horizontal, dividing it in half by the mean, and then in the vertical, dividing it in half by the mean. And what do you see here? Most of the time, when x trends above its mean, so x is above, where's y? Mostly it's here, but sometimes it falls below. And when x is below its mean, mostly y is below. So it's like the first case, when x is high, y is high, mostly. And when x is low, y is low. But not as good as r equals 0.1, right? I mean, r equals plus 1. It's closer to, it's not as close as 1. Let's just say 0.8. And I have some others to look at. I made one that was just scattered all over the place for you. So this is just that one I gave you. I'm just recreating it. So this is the one that's scattered everywhere, and you can do the same thing, and you'll see that there's no pattern. When r is above, so I'm cutting it in the middle this way and this way, and you see there's no exact pattern. I'm going to draw one more here. Oops. There's no predictability. When x is high, y can be high or y can be low. When x is low, y can be high or y can be low. So it's not so predictable. In this case, if you were to actually calculate it, r would be 0, but you probably shouldn't. You should just not calculate it and say there's no linear pattern. Okay? Alright, so that's all I really wanted to say about that. And the reason why I'm emphasizing that is just to help you remember these formula, that you're going to be thrown a lot of formula. And this is what's behind them, okay? This one is negative. It's perfect negative correlation. This one, which is more scattered than the one above, but it's kind of going down, I said r was negative 0.5. So it's closer to 0, but it's halfway between 0 and negative 1. And then I said that this is a nonlinear relationship, and you would find that if you were to do the calculation, you would probably get r equals 0, but you shouldn't, right? You shouldn't calculate the r when you have a curved relationship. But it does have a relationship, it's curved, and we don't talk about that in this class, but in higher level classes or in life, you might want to estimate that. Okay? So you would estimate it with a curve. That says relationship. I'll just erase it because it's messy. Okay, so now let's go look at the formulas and wrap this up. Unbelievably, took this long. So now what I'm going to tell you is going to blow your mind. And that is that you have several formula for correlation. The one I showed you is just to illustrate what correlation is, but you're not going to use this version of the formula, okay? All you're going to do is use your calculator, all right? But you need to know the formula because you need to know it for ex-ante returns. You need to know how to get it for either case by hand, but really you're going to use your calculator. So I start here with the covariance. Covariance is, whereas, okay, this is the covariance of x with itself. So covariance is the more general. Okay, this is the variable x with another variable y. So covariance is actually going to pick up the direction and the strength of a linear relationship as well. However, the problem with covariance, and the reason why we have another measure that we use, is because the result of calculating the covariance from data set to data set is unclear. We don't know how to interpret as easily as we do the correlation, because the correlation, the way it's calculated, this is correlation that I want you to use this formula, okay? So this can be derived from the one I showed you. Correlation is essentially a standardized covariance. That's what it is. It reduces whatever the covariance was to an index between -1 and 1, and we know how to interpret that. Okay, if we just use covariance, depending on the data, the number that we got, we'd know the direction. It would have the same sign as r, just like the slope has the same sign of r. It tells us the direction, but not the strength as easily as standardizing it would. So correlation is the standardized covariance. And I can prove that by expanding the formula. You see, this is covariance here. Right? And then dividing by Sx, Sy. And those are just numbers. Sx, Sy are just values. They're the standard deviation. I can move those. They don't have an, I mean, they're just constants is what I want to say. So I can put it here, I could put it under here, which is what I do to get this version of the formula that you may have seen. Alright, so they're all the same. The one I just talked about to illustrate what correlation is the same as a standardized covariance. So there you go. Those are the sample statistics for financial data. Mean, standard deviation, covariance, correlation. So there's a relationship. So if I ask you, you can calculate correlation in your calculator for historical data. And since you have Sx and Sy from your calculator, you could also find covariance. Remember that. I'll make a note. You can compute covariance xy from r, sx, and sy in your calculator. Okay, so you can get them all from your calculator, and if I ask you for covariance, you can give it to me using this. You would actually just multiply r by sx and sy store them or write them down and you can get them. Okay? So the only formula that remains is this one. I just ruined it. Let me make it bigger. This is the formula for slope. Now you're like, why do I need a formula for slope? Isn't it just change in y over change in x? If the observations, if the data points do not fall directly on a line, so you have a scatter plot like the ones, like a scatter of data like we were just looking at, then you have to use statistics to estimate the slope. And the calculation of the slope, you learned this in statistics, but you might have forgotten, is RSY divided by SX. And it's really handy if you remember the mnemonic risk R, then you know it's SY over SX. This helps you remember the Y comes first and then X. And in fact, this slope gives us an indication of risk. It gives us an indication of the risk associated with, in this case, BCE stock, and including it in a portfolio of other stocks that mimic the market portfolio. I'll explain that in a second. So this is it. You just need R, SY, and these are all on your calculator. Okay, these are for historical data. You can get these all from your calculator. So if you remember this or not, notice what I told you. Both B and R tell you the direction. R tells you the strength. They both have the same sign, right? SY and SX will always be positives because they're square roots of the variance. These will always be positive numbers. So that means that B has the same sign as R. Make another note. I already said it above. They have the same sign because they both indicate the direction. So R and B are intimately, they're related. Okay, but they tell you different things. R, direction and strength. B tells you direction. Now let's talk about the risk for a moment. So what you have here, if the market is up, so if we are in an expansionary economy, this would be reflected in the market. High returns, right? High returns, BCE does twice as good, which is great. All of these are positive. But if this pattern was consistent with negative returns, so let's say there was a drop in the market, there were losses, so these would actually be negatives. If these were negatives and the pattern continued, BCE would have negative returns. And not only negative returns, 2 times the negative returns. Okay, because it's the same pattern. Now, I don't know that the pattern is going to remain like that. I mean, I just made up these numbers, but that's the effect of the slope. Okay, it's great in good times, but not so bad, not so good in bad times. When the economy does poorly, you do, with BCE, you do 2 times worse. All right, we're going to talk more about that. These are all the formula. You're going to get lots of practice. I ask you to calculate all these statistics, and you did it very easily with your calculator, right? but you need to practice by hand. So I also gave you the formulas, everything computed. So practice making those calculations. I'm going to tell you a little bit trick about that in a second. All I want to say is, what about ex-ante data? Remember, this is data that is predictive. It's using industry information, forecasts for BCE and forecasts for the economy to develop a discrete distribution. Here it is. If the economy does great, and there's a 40% chance that it does, the market returns will be 14%. So for every dollar invested, or for every $100 invested, there's $14 return over the coming period. BCE will return 30%. If it's a normal economy and there's is the greatest chance of just a normal economy, 50% chance S&P, the market will return 8% and BCE 18%. Worst case scenarios, a recession happens with 10% probability. S&P has the worst returns, and so does BCE. So there is a trend here, but how do I calculate the mean, standard deviation, covariance, correlation, and slope when data is ex-ante? Well, I put all the formula here that are equivalent. You have the weighted mean, the weighted standard deviation, the weighted covariance, the weighted correlation. I have all the versions of it. You probably just do it this way. It's the easiest, right? So notice the notation is all the Greek letters. Don't let that disturb you. But now I'm going to use Greek letters because this represents a distribution or population results. Okay? And I even have this, the slope. And now you see why this is often the slope of financial data, where you have the market returns on the horizontal axis and asset returns on the vertical axis. We refer to the slope relationship between them as the beta. Still, we calculate it and interpret it as a measure of risk, of including this company asset, this asset, in a broader portfolio of risky assets. I also gave you the formulas, the solutions for that one. So in the handouts, I just want to show you, you're going to practice this, because if you don't have an HP, you got to do this manually. So I'm going to pull up these ones. You have to learn how to do this manually anyways, okay, for this class, but just not for too much data. There's 5 data points here. I at least expect you to do it for 3. Okay, so for ex-ante, I only gave you 3. My recommendation, and here I am calculating the mean, the standard deviation, and what I've done, or what I've tried to do, but my columns got messed up, is to write these out in columns. If you use the columns, all my columns got bumped. Let me use the other. I'm gonna go get the other one. Looks better. I hope so. I'm not sure why. So ex post or historical are the same term. So you see, I tried to use columns here. So all you're doing in calculating and writing these down is columns. So this is for the variance, right? Because you're going to have to do the deviations from the mean each time. So it's going to be this column, for x is this column, minus the mean all the way down, and then square, 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 and average with, well, 4. Can you guys see that? Okay, so that's how I recommend you do this much quicker. Notice in calculating the covariance, if I ever ask you the covariance, you go like this. I know you probably want to buy an HP calculator now, but what can I say? You yeah, in the HP you can get these. I send the notes for HP to people if they want it, but you do have to do it the longer way for the test, so I do need you to know how to do this for the test next Saturday, not this coming one. So that's the practice for those. It turns out that in this case, in the ex-ante data, or should I tell you? Well, it turns out in this case as well, the slope turns out to be 2 and the correlation 1, but you can't draw it. But you can compute it. So it's not like, because every data point has different significance, it's not literally like the one above. But it turns out the numbers were chosen in a way so that you're still going to have a slope of 2 and an R of 1. So the R of 1 means that it's a strong relationship, and the 2 means that's the direction of the relationship. Okay, that the returns are double. Okay. So that's a lot of formula, but I hope I broke it down, that you see that all you need, you already understand the mean, the standard deviation, correlation, standardized is the covariance, standardized is the correlation, and then this is the formula for slope. Just to make one more point. In this case, you could have calculated the slope easily, right? As rise over run, but if you have a scatter, if you have a scatter like this, scatter plot, the line that's associated, that you're saying the slope, the slope that you're finding goes on this line. This line is known as the least squares prediction line, right? The prediction line. It's not it's a mathematical line. It has it's still like the formula is still, or the equation of the line is still a plus bx, but it's not exact, okay? The points aren't even on it in my drawing here. And the slope you're finding the quality of the slope you're finding will depend on how good the R is. So the better, the stronger, the closer R is to negative or positive 1, the more significant the slope. You know what I'm saying? So this one, it's not, it's really, really scattered. So the prediction line is the line that fits closest to all the points. Your calculator will take care of all that for you, and the formula takes care of all that for you, the risk formula, okay? So it's finding the slope on the line that fits best to all the points, closest in that the distance, the residual distance from all the points is minimized. The square residuals are minimized because you have some above and some below. Same problem we had with the mean. Some are positive and some negative, so we have to square them. Anyway, you don't need to know any of that because you have this formula. But that's where the formula comes from. You use this formula when the dots don't fit on a line, okay? This will give you the answer. And that will be most cases. What else do I want to tell you before you go? So you have those problems. So I'm going to ask you, you're going to do this. What you're going to do, oh, let me just show you this. So these are the formula, the same formula, okay? They are the same formula but with different letters. I use the letters that I used in the notes, but I'm hoping, I wrote them all here so you can verify, but you see, this is for ex post data, but it's the same sort of thing. This is the sample mean, but look, I use R for return for finance. This is the sample standard deviation, and I use a hat for an estimator for sample standard deviation. R's for returns. Here's the covariance, R's for returns, and all this crazy notation. Don't let it intimidate you. It's just what we did. It's just the X and Y's. Just remember that in finance, when we work with this, we're putting always the market returns on X, and on the Y-axis, we're putting the asset or the company stock. Oh no, it's frozen again. Dear. Okay, I'm going to try and get it up so you can see what I wrote on the last slide. I don't know why that's happening. Give me a moment. Sorry if some of you have to go, but you can come back and watch it later. So I have to get out, and it's funny because it says it's mirroring. I don't know. Why is it doing that? Okay. I'm here. I'm just I don't know why that happened. Okay, I'm back. It looks like it's reading again. Thank you for letting me know, and I apologize. Yeah, it's coming back. Okay. So this is what I wrote when I was talking. Okay. So what I was saying was in statistics we use this formula to get the slope, not like you know, change in y over change in x, because all of the points don't fall in the line, right? They're all over, they're scattered. But the slope we find is the slope of this line called the prediction line. This is the line that fits closest to all of the points. How do you find it? You use this formula. This formula has figured out all of those things for you. Okay, so this is the result of optimization, positioning this line so that it's perfectly closest to all of the points in both directions. So it's kind of like the mean, but in two directions. All right. So that's what this formula does. It fits the line, the prediction line. It gives you the slope for that prediction line. And the next thing I was saying to you was, and I'm sorry if some of you have to stay over and it's late, but I want to say to you a couple of things. Exactly, Andre. So that it minimized the sum of the squared residuals. Exactly. I was avoiding getting into the details, but yes. So it's coming back to you, right, guys? That's what I'm hoping. You've seen this all before. So the last thing was this handout 5. Oh, I don't even know now. What was this that I opened? It's 5.7. So this is 5.7. These are the same question, but what I've done is change the notation to finance notation. So it's virtually the same formula. All I've done is gone from X and Y's to R's, and RM for market, RI for asset. That's all that's happening here. And don't let it intimidate you. 5.7. Okay, so you have the average here, average return, because we're talking about returns in finance. I use the notation R bar because this is like a sample. And then same here, this is like an estimate or a sample standard deviation. We use the hat. So you see different letters, but it's the same formula. Same formula. This is the covariance. You don't have to rewrite these formula, okay? They're just meant to communicate to you what to do. But so when you can read them, I'm showing you these are the formula in the notes, and in the text are similar. Correlation. This is just the standardized covariance. And look, I'm using Greek letters, so now I have the sigmas. Don't let the sigmas bother you. And here, remember, oh yes, the one thing to say here, remember this is, what is risk? What is beta? Beta is R SY over SX. So Y is always the asset. That's why I is on top, because I is the asset. or like the firm's assets, the stock, and M is for market. I'm trying to fast track you guys. I hope it's working. So this is market, you see, because that's on the x-axis, times R, and this is the notation for correlation between the asset and the market portfolio. So hopefully you guys can make the translation from the basic statistics formulas that you learn to finance formulas. They're just borrowing from here and applying it to financial returns. For the ex-ante data, similarly, I'm replacing everything with R's. Now, because this is like population data, I got rid of all the hats. Like the hats are estimates or sample results, but now I'm using purely Greek letters. Okay, because this is indicative of a distribution representing a population. So these are population results. That's how we treat them, for a distribution. So I want you to read everything I gave you before next class, and I'm going to send you some more things so that we can launch ahead. We really gotta catch up now. What else did I give you? I gave you 5.8, which are the notes. So you can read through the lecture notes yourselves now. It's just an example. No, not this one. Oh yeah, wait. Let me see. I'm misspeaking. Yeah, you guys should read through these, and then it'll make it easier for me to make the presentation. I should go fast with this on Tuesday. So those are the notes. 5.8. Sorry, I'm just going through what I gave you. And a review exercise 5.9. So you guys can definitely read ahead, but I will cover this on Tuesday's class. Okay? Sorry for all the freezing. I don't know what's going on. But I encourage you, okay, because this is a long weekend. I know you guys are going to want to rest after the test. But if you want to read ahead, I've given you enough material that you can work ahead. And then Tuesday will be like a review for you. All right, so if you have any questions for the test in advance, please text me or email me in a separate email, not a reply email. Create a new email and ask me your question, and either I can respond by email, or I can call you, or we can meet by some virtual application, FaceTime or Zoom. Did I say five? Did I give you 511? What else did I give you? I gave you 11. Yeah, 511 is yeah, you can read 511. You can read 511. Go ahead. So some people who are comfortable can read ahead. Okay? But I need to finish all of that on Tuesday, so if you read ahead, that would be great. Yeah, we're going to review all that on Tuesday, and then I'll have more for Thursday and lots of exercises. My goodness, we have lots to do for the upcoming test. Okay. Well, thank you for staying over, and I apologize for all the freezing. I'm not sure. I think I got to do my update. I'm going to do the update. I have 5 days. It should update by then. So review this video. I'll put the timestamps in to make it easier for you to get through. I hope that helped with the statistics. and it's less intimidating. Let me know if you need any additional help. So good night. I'll stay on for a minute or two if people have questions. I never saw this before.
And they ran commercials like this like all the time.
Oh my god.
Like all the
like
time.
when? In the 2000s? Like when?
Yeah. I don't know when this one is from.
No, I never saw anything like that.
I don't think it's old. Yeah,
like on TV?
Yeah.